B. Naresh, working as assistant professor in EC department. And today's topic is common base configuration with its characteristics here. So in the last sessions, we discussed that transistor operation here. So from that, we defined that the transistor contains three terminals here, namely that is emitter, base, and collector here. And based on the construction, then we have the two types of the transistors here. One is NPN transistor, another one is PNP transistor here. So we can choose any transistor while making these configurations here. And we are having the three types of the configurations. That is one common base configuration, another one is a common emitter configuration, another one is a common collector configuration here. So in this session, we are going to observe the common base configuration. Along with, we need to identify the characteristics of transistor under this common base configuration here. So from this point of view, this common base configuration is also called as ground base configuration here. And from this representation, base terminal is acts as a common for input side as well as the output side here. So if the base is a common, and out of the three terminals, and the remaining two terminals, either it is acts as a input or a output terminal here. If we mean the base is a common for input side and output side, the remaining two terminals are emitter and collector. So from this emitter and the collector, we need to identify that. So which terminal is used as a input side and which terminal is used as a output side here. So for this representation, now we are going to choose the emitter is acts as a input side and the collector is acts as a output side. With respect to your common terminal is your base. So that is the reason. So we represented your emitter is the input terminal and the collector is the output terminal, along with the base is the common terminal. Then, so we need to find out from this representation the input terminals is in between emitter as well as the base, and output is measured in between collector and base here. And from this, we need to design a common base configuration here. So for this case, so let us consider, here I consider the NPN model here, and this is the N-type material and a P-type material and N-type material. And there is intersecting of two PN materials, and that is called as the base. And another end, one end is represented with the emitter, one end is represented with the collector. So when we form these two PN junctions or back to back, it creates the junctions. One is across the emitter side, one is across the collector side. So here this is acts as a one PN junction, and here this is acts as a another PN junction here. Now the aim is to you, we need to take here the emitter is the input side with respect to your base, and the collector is the output side with respect to your base. Then we need to measure some biasing here, and here in between these two, we are going to measure a potential difference between emitter and the base, that is represented as your, so here it is represented as VEB here. And if we measure the potential difference between collector and the base, that is represented as your VCB, where this third letter indicates the type of configuration we used here. So where the B is used as a common base configuration here. So from this, here I use this NPN construction is replaced with a transistor here, NPN transistor model here. And here it is represented as, again, this is VEB and VCB here. And across the base current is represented as your IB. And across the collector, it allows the collector current, that is represented as IC. And this is your across the emitter, it allows the emitter current is I. Now I'm coming to you. So here I consider this NPN model, and here we connected as two PN junctions are back to back. Then it formed the two junctions. So one junction is between emitter and a base. Another junction is formed between collector and a base. So that is the reason. Here it shows that two depletion regions are formed while constructing this model. So one depletion region is formed between base and emitter. One depletion layer is formed between base and a collector. Then, if you recall the transistor, so what is the meaning of transistor? Transistor means it transfers the low resistance, means a signal is a transfers from low resistance input circuit to the high resistance output circuit E. So that is the reason we need to satisfy the input side. We need to offer a low resistance device, and output side we need to offer high resistance C. To satisfy the definition of the transistor, it transfers the signal from the low resistance input circuit to the high resistance output circuit. That is the reason we need to offer the input side, we need to offer the low resistance, and output side we need to offer the high resistance. And how we are going to make this biasing or to satisfy this transistor phenomena here? For this case, if you observe a PN junction diode, and here this is the P type material, and here this is the N type material here. So if a P is biasing through with the positive potential of the battery, and N is connected to negative pole of the battery, and we know that here, and with respect to this force, here the PN junction diode is acts as a forward bias here. And we know that when PN junction diode is under forward bias, it offers a forward resistance here, and that is represented as RF. But we know that here, so under the diode is under the forward bias, it offers very small forward resistance. That is the reason. So RF is very small here. And similarly, if the PN diode is operated under the reverse bias, so means how to operate the reverse bias here. Let us take again, this is a P type material, N type material. With the P is connected to negative pole of the battery, N is connected to positive pole of the battery. So from this, we can say that this diode is acts as a reverse bias diode. So when the diode is under reverse bias, it offers a reverse resistance here. It is represented as RR. So under the reverse bias, there is no conduction takes place across the PN junction diode. That is the reason it offers very large reverse resistance. So hence RR is a very large here. So from these two observations, we observe that when the diode is a forward bias, it offers very small forward resistance. If the diode is operated under the reverse bias, it offers the very large reverse resistance here. That is the reason. So by using these two phenomena with respect to your diode operation, so here I'm going to show that how this transistor transfers the signal from the low resistance input circuit to the high resistance output circuit. So to satisfy for this condition, so input side we need to make the low resistance circuit here. So hence in between this emitter and base junction here, let us take this is the emitter and this is the base junction. So in between this emitter and the base junction, we need to offer a very small forward resistance here. So how you are going to offer this very small forward resistance across this PN junction here? So that is the reason. So we need to make this particular junction is as a forward bias here. So if this junction is a forward bias, we know that that particular junction is offers the very small forward resistance here. Hence, we need to make this biasing. So if you consider the input side, the junction here, the base material is P and emitter material is represented as your N type. Now, in between this emitter and the base, we need to offer a forward bias condition here. Hence, here now again the base is connected with your positive pole of the battery. Why? Because of that here this material is a p-type material, and we know that when the p is connected to positive pole of the battery with respect to your cathode, then we can say that that particular diode is acts as a forward bias diode. So that is the reason this base terminal I made with a positive pole of the battery. And you're coming to your emitter. So emitter side is N here. N is connected with your negative. So due to this approaching of external force between the emitter, hence here I represented as V suffix EE. And due to this energy here, this particular PN junction is acts as your forward bias diode. So when it is a forward bias diode, and we know that this particular junction is offers a very small forward resistance. So that is the reason. So this is the input junction, and this input junction here it is acts as a forward bias. Hence, it offers a diode forward resistance should be very small. And similarly, then to satisfy this transistor operation, so output side we need to offer the high resistance circuit here. So how we are going to make a high resistance across the PN junction here? So that can be done through that PN junction diode is operated under the reverse biased configuration here. So hence, output side, the two terminals are involved. One is collector with respect to your base. And this collector and the base contains a p-type material and your n-type material. So in between this collector and the base, we need to make a reverse biased configuration here. So if you observe this collector terminal, the collector is made with n-type material. So hence this n-type material is biased with the positive pole of the battery, and then base is connected with the negative pole of the battery. So that is the reason with respect to this biasing. So when the n-type material is connected to positive pole of the battery with respect to your cathode or anode, so what happens here, this particular region, this collector base junction is acts as your reverse bias. So hence, so this output side we taken as a reverse bias. Hence, it offers a very large reverse resistance here. So due to this approaching of VEE and VCC, we made as a input side, we defined as that input junction offers the low resistance here. And due to this biasing of VCC, output side, then the circuit offers the very large resistance. Hence, this given model or a transistor transfers the signals from low resistance input circuit to the high resistance output circuit here. So this is a construction or configuration of common base configuration by using the NPN transistor here. So after this biasing, then we need to identify that one. So based on this common base configuration, we know that the emitter is acts as a input terminal and the collector is acts as your output terminal here. Now we need to measure a voltage between means a input side. We need to measure the current as well as the voltage. The voltage between emitter with respect to base and the current is measured across your emitter. So whatever the current we are going to measure across the emitter, and that is here it is represented as your I. Similarly, we need to observe the voltage across the emitter with respect to your base. It is represented as, so that is VEB. It indicates that this VEB indicates that the potential difference between emitter and a base when this particular junction is biased here. So when this particular junction is a bias and we observe this a voltage across the emitter with respect to base, that is represented as a potential difference between emitter and the base. Similarly, the output side, and this output junction is reverse biased here. Now we need to measure the output voltage and the current across the collector with respect to your base. Common terminal is the base here. So if you want to allow the current for this transistor, this is the current flow direction, and this current is represented as your collector current, it is represented as IC. So similarly, we need to measure a voltage across a collector with respect to base, that is represented as your VCB here. And here, this VCB indicates that the potential difference between collector and your base here. So these are the parameters we are going to observe by using the characteristics of the common base configuration. And we know that this is the in this NPN transistor, due to this biasing energy, electron is diffusing from this N type to means emitter to base to again collector here. So that is the reason current is flowing opposite direction here. So here the current is flowing from anode to cathode here. So if you consider the PN junction here, so hence this is the current flow direction here IA, and this current here this is IA, and this current is leaving towards two terminals. One is leaving towards the base and it is constituted with the charge carriers of the base, then it contains a base current, and similarly and it leaves towards your collector side, that current is represented as your IC. So this is some operation about common base configuration here with respect to your biasing conditions here. So by using this configuration, now we are going to analyze the characteristics of your common base configuration here. And before going to this, let us consider. So for any transistor, so either NPN transistor or PNP transistor, and whatever the configuration. So we are in three types of the configurations: common base, common emitter, and a common collector. We need to define a current gain parameter here, that is represented as a DC current gain in this BJT here. So and we have the three different configurations. That is the reason for each and every configuration we need to identify the current gain of that particular transistor under a particular configuration here. So in this common base configuration, that DC current gain is represented as alpha, or it is also represented as some alpha DC. And in this case, the current gain is defined as it is a ratio of output current to the input current. The DC current gain is defined as the ratio of output current to the input current. So here we need to find out that which one is acts as the output current and which one is acts as the input current here. So based on the configuration, we know that the collector terminal is acts as the output side and the emitter terminal is acts as the input side. That is the reason. So here this alpha DC or a DC current gain under the common base configuration is represented as alpha is equal to, it is defined as the ratio of output current is collector current to the input current is your emitter current here. So from this, if you want to write again, so based on the transistor operation, we know that the emitter current is represented as the summation of base current and your collector current here. So why? Because of the emitter emits the charge carriers to allow the conduction in a given transistor here. From that point of view, whatever the charge carriers are emitted by the emitter terminal, and those charge carriers are diffused towards base and a collector to produce the current here. So from the representation, here it is defined as the total emitter current is a summation of base current and your collector current here. But we know that based on the doping levels and based on the regions of the transistor, and if you observe the doping levels here, so we know that emitter is a heavily doped, base is a very lightly doped, and a collector is a moderately doped here. And if you observe the regions, base region is, so they are the doping conditions. And if you observe the regions or the widths of the terminals here, the base width is very thin and collector is large region. emitter is moderately region. So due to these regions and due to these doping levels, whatever the charge carriers are emitted by the emitter, and those charge carriers are diffusing towards the base and the collector. And from this process, so very small amount of the charge carriers are constituted with the base, and the remaining all the charge carriers are constituted with the collector charge carriers here. So that is the reason from that representation, the given transistor or a BJT, it offers very small base current compared with your collector current. So that is the reason we taken as this another approximation here. The base current is a very small compared with your collector current. We can write this IE is approximately equal to your IC. And again, and from this DC current again, if you want to write in terms of the gain parameter, so from this relation, so we can write this IC is equal to alpha times of your IE. But we know that in a transistor, so in a BJT, the conduction depends upon the both the charge carriers, that is majority charge carriers as well as your minority charge carriers. So if you consider the a minority charge carriers here, or the collector base junction is your open circuited here. So if in this common base configuration, we made as the input junction is a forward bias and the output junction is your reverse bias. So in that configuration, the output junction is a collector base junction, and we made as this collector base junction is a reverse bias. So if it is the reverse bias, it acts as the open circuit, means it allows the a reverse saturation current here. And that reverse saturation current here it is represented as ICBO. So here this ICBO indicates that when the collector base junction is a reverse bias, it acts as the open circuit. It allows some reverse saturation current to the effect of minority charge carriers, and that current is represented as your ICBO. So if you want to write the current in terms of majority as well as the minority, then here it is represented as IC is represented as alpha times of IE plus your ICBO. So this is a mathematical relation of collector current under the common base configuration here. Now coming to your characteristics of common base. So whatever the transistor and whatever the configuration in this BJT, it have the two types of the characteristics here. So one is represented as input side, that characteristics are represented as input characteristics. Another one is the characteristics absorbed across the output junction, that is called as your output characteristics here. Now we need to see, now we are going to observe what are the input characteristics and how it behaves here, and what are the output characteristics, how the transistor behaves under this common base configuration here. Now coming to first the input characteristics here. So in this case, and again we need to consider a common base configuration here. And to construct this common base configuration, we need to follow the biasing approaches here. And here we need to approach the input side, we need to maintain that input junction should be a forward bias, and output side, the collector base junction should be a reverse bias D. To identify these characteristics, suppose if you observe this, so in this case, let us take, these are some parameters here. So if you observe the input side, so what are the parameters we need to plot here? So the characteristics should be plotted between your input voltage, that is your VEB, and the input current is your I. Means we need to plot the input characteristics. So this input characteristics are plot in so VEB versus IE, and while maintaining that output is constant. So from that representation, so let us take, So here I representing in terms of measuring parameters here. And here I consider the same configuration. So this emitter base junction is a forward bias due to this approaching force with respect to your VEE. And a collector base junction I made with a reverse bias with respect to biasing approaching of VCC. And we need to observe the input current that is across the emitter, that is I represented as IA. And input voltage we need to measure between emitter and the base, that is represented as your VEB. So hence we need to plot the characteristics between VEB and your IE while maintaining this output is a constant. So means VCB we need to take. So by making this VCB is a constant, we need to identify the characteristics of your input junction. Similarly, if you want to observe the output characteristics here, so means if you observe this, what are the parameters are available at the output side? Means we need to measure the output voltage and the output current. So the output current is represented as across the collector terminal, hence we need to define with IC. And output voltage, it should be represented across the collector and the base, that is represented as a VCB. Means that the potential difference between collector and the base is represented as your VCB. While making the input is a constant. So then here what is the input here? The input is means IE. If we want to plot the output characteristics, the characteristics are drawn between VCB versus your IC by making that IE is constant. Now we'll see the first how to plot the input characteristics here. So by making this VCB is a constant, let us assume that if a VCB is a 0, so let us consider, and this is your NPN transistor. I consider this is the N, and this is the P, and this is the N here. And input side we need to make the forward bias. This is the plus, and this is minus, and this is represented as a VEE. And similarly, the output side we need to make a reverse bias. N is connected to positive pole of the battery, and it is represented as a VCC. And this is collector, and now here this is IE, and this voltage across between emitter and the base is represented as your VEB. Now I made this VCC the constant. So if you look at this configuration, so in this case, let us consider. So when the two junctions are formed here, so let us consider this is the internal depletion layers here. And here I made this VCB is a constant. So means suppose the first case VCB I consider as a 0, or VCC is approached as a 0. The 0 means due to the 0 voltage, a depletion layer is formed between collector and the base. Now if you are changing this VEE, so what happens here, the input junction is acts as your forward bias. Means it looks like a normal PN junction diode forward bias. So what is the PN junction diode forward bias? When the PN diode is under the forward bias, whenever the applied voltage is reached to your cutting voltage, or your applied input voltage is larger than the given cutting voltage, then conduction takes place here. Means that current will be increases rapidly whenever the biasing voltage is reached to the cutting voltage here. So from this phenomenon here, so the input junction is a forward bias, hence now we can observe that this particular PN junction diode is acts as a forward bias. So if the PN junction diode is a forward bias, we know that when your applied voltage reaches to cutting voltage, up to this cutting voltage, there is no conduction takes place. When it is reached to cutting voltage, then it starts the conduction, hence the current is linearly increases here. So same characteristics are observed by using this input characteristics. But what happens if a VCB is increased from the 0, means when VCB is greater than of some 0. So the VCB is increased from the 0 means we are increasing the large reverse voltage. So due to this large reverse voltage, so what happens here? So we know that when the PN diode is operating the reverse bias, so if the large reverse voltage is applied, the depletion layer is increases here. And coming to here, the depletion layer is increases here when VCB is increased from the zero. So means this depletion width is increases towards collector side as well as your base side. But here, so if you assume, suppose let us assume the P type and N type materials are equally doped, then the depletion layer is also formed equally at the P type material and your N type material. But coming to this BJT transistor, here the three terminals are differently doped here. But here, and we are talking about this output side, the base is a very lightly doped compared with a collector. That is the reason. When this biasing voltage is increased from the zero, the more depletion width is penetrates to your base side compared with your collector side. So that is the reason. More depletion width penetrates toward this base side compared with your collector. Due to this, what happens here? The base width is a decreases here. So whenever the base width is a decreases, what happens here? So fastly this charge carriers to cross the emitter to your collector bypassing the base. So that is the reason. At this point, whenever the VCB is increased from the zero, the conduction takes place earlier compared with your when VCB is zero here. So that here I am going to show you. The same points I represented here. This is a VCB is a zero, and when VCB is a greater than 1 volt, so what happens here due to that reverse voltage, more depletion region is a penetrates towards the base. Hence, the conduction takes earlier compared with this VCB is zero. And similarly, if you coming to your output characteristics here, so how to plot this output characteristics? The output characteristics plots in between VCB versus your IC by making the input current is constant. So here the input current is IE. So we need to maintain IE is a constant. By making the IE is a constant, then we need to change this biasing voltage. Then note down the corresponding collector current and your corresponding collector and base voltage, means the potential difference between collector and your base voltage. So before to observe this one, suppose if you want to plot this characteristics here, and x-axis should be represented as a voltage, that is represented as a VCB, and a y-axis is represented as your IC. But in this common base configuration, we observe this, the IC collector current is approximately equal to your alpha times of your I. So this IC is approximately equal to your alpha times of Vi. In a common base configuration, alpha is lies between 0.95 to 0.98. Why? Because of that. Base is a very lightly doped here. Due to that, so the 2 to 5% of the charge carriers are constituted with the base, and the remaining charge carriers are constituted with your collector. So based on this alpha representation, if you know that suppose if only the 2% of the charge carriers are constituted with the base and the remaining charge carriers, means suppose let us assume that emitter is emits the charge carriers. So let us this emitter emits the 100% of the charge carriers. Out of this 100% of charge carriers, the 2% of the charge carriers are constituted with the base. So remaining 98%. So 2% is a constituted with the base, and the remaining 98% is a constituted with your collector. From that, we know that alpha is defined as it is a ratio of output current to the input current. So means IC means it contains the 98% and IE is 100%. So hence the maximum value is a lies between 0. So here the alpha value is 0.98. So that is the reason. And based on the construction of the transistor, so on that, so 2 to some 5% of the charge carriers are only constituted with your base. So remaining charge carriers are constituted with your collector. So that is the reason. From that representation, alpha is a lies between always 0.95 to your 0.9. So from this, we know that IC is approximately equal to your I. If I consider that alpha is a 0.98, that is approximately equal to I. Then, and by making this IE is a constant, And let us take coming to a collector based junction or output junction. And here this output junction is accessed under the reverse bias here. And we know that if particular PN junction diode is operated under the reverse bias, we know that there is no flow of conduction. At this point, the diode is accessed the open circuit. So hence, the diode is accessed the open circuit under the PN diode is reverse bias. And at this point, we need to find out the output voltage. And from this representation, the output voltage is proportional to your V when the diode is reverse biased. So hence, so at this point, under this reverse bias, if the VCC increases, the proportionally the same voltage will be absorbed across the collector and your base. But the collector current is trying to reach equal to your emitter current. So hence, if it goes on, you are increasing the VCC. VCB is also your increases here, but the collector current is trying to reach your equal to your emitter. Let us take, suppose if I consider this IE is a 1 milliampere, IC is also trying to reach only your 1 milliampere. Hence, so this is the 1 milliampere and this is also your 1 milliampere. So that is the reason. From that point, here I shown this output characteristics of common base configuration here. So let us take this x-axis is represented as a VCB and a y-axis is represented as IC. By making the IE is a constant, suppose this I taken this IE is a 1 milliampere and this node is a 1 milliampere and VCC is increases, this is the biasing is increases here. So what happens, VCB is also proportionally changes, but collector current becomes to your equal to your emitter. And that is the reason the constant will be, so constant current is flowing through this transistor. Suppose if I is a 2 milliamperes, then collector current is also trying to reach 2 milliamperes. If the 3 milliamperes is trying to reach 3 milliamperes. Now let us take, and this is the voltage is the biasing through the VCC. If VCC we need to apply the suppose less than 0 voltage, means what happens here? If you are passing the negative voltages, then what happens here? That particular junction is acts as your forward bias. So if it is a forward bias, when we are approaching the negative energies through this VCC here, then it is acts as a forward bias. If it is a forward bias means, then start the conduction from minimum to your maximum. So that is the reason I represented these lines here. Now you can observe here, at this point, emitter base junction is already forward bias, and due to this approaching of the negative energies across the biasing of the collector base junction, then this collector base junction is also becomes to forward bias. And we know that when emitter base junction is a forward bias, collector base junction is a forward bias, that particular region is called as your saturation region. Similarly, and from this node to this node, your emitter base is already forward biased and a collector base is your reverse bias. Hence, that region is called as your active region here. And how we can say that the region is cutoff region, means both the junctions are your reverse bias, then we can say that that particular transistor is operated in your cutoff region. Now you can observe here, when IE is 0 or less than 0 here, means when the current is 0, input current is 0, means when that particular input junction is operated in the reverse bias, there is no flow of current across that particular junction. But here we are taking that here the current flowing across the emitter terminal is 0 or less than 0, means that at that particular point, that particular emitter base junction is acts as your reverse bias here. So if it is the emitter base junction is a reverse bias, there is no flow of charge across the emitter terminal. That is the reason here we represented that emitter current is a 0. Under this point, your emitter base junction is a reverse bias. Already this collector base junction is your reverse bias. Now we can say that, so both the junctions are reverse bias, hence this particular region is called as your cutoff region here. So these are the some characteristics of common base with respect to your input and your output. So up to this point, we observe this common base configuration and its characteristics here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.